A blockchain is a replicated deterministic state machine. So let's build smart contracts by visual programming as finite state machines using global or local functions. If you have watched previous videos, you know that we already have the most flexible blockchain. You can already write smart contracts in Solidity, Python, JavaScript, AssemblyScript, Rust, Golang, because our execution engines are based on interpreters compiled to WebAssembly. So today you will get a taste of the first state machine interpreter that we are preparing. But first, let's start from the basics of what and how we can represent visually. In order to have a visual language, the basic building blocks are nodes and edges. But there are different ways to interpret a graph as a smart contract on-chain. We can have nodes as states and edges as functions, and we call these state machines. But we can also have nodes as functions and edges as states, and we call this a data flow diagram for data flow programming. The states are the inputs and outputs of the functions represented as black boxes. And we have built tooling for data flow programming for smart contracts before. We called it pipeline. By using a database of smart contract functions that we called lens, you could pick and add functions to your graph. And then the graph was translated into a representation that could be interpreted by our smart contract interpreter, or it could output a standalone smart contract. But the same graph would also create a user interface for you and could be executed in JavaScript. This type of cross-contracts composability can be applied in different domains like decentralized finance. And you can watch our videos of our pipeline iterations from 5 years ago. So now we are going the complementary route, state machines. And we are going to use an external project for creating the state machine diagram, the stately visual editor, and then run the state machine in our WasmX interpreter on our Mythos blockchain. We start with two states, unlocked and locked, and then define two events for transitioning between these states. Lock and unlock. We also define a counter variable in our context and initialize it with 0. And we will make it so that you can only increase this counter when the state is unlocked. So here we will add a self-transition and call this event increment. And we will also define an action named increment, which is a custom action that will receive the counter value and will increment the counter with 1. So this means that for every increment event, we will increment the counter with 1, and we can only do this while the state is unlocked. And this is the JSON configuration object that Stately has generated. And we will copy this part without the types and action definitions. Now, the state machine interpreter was written in AssemblyScript and compiled to WasmX. So we have some limitations around parsing JSON. So we will slightly modify the JSON that we have from Stately that we will paste here. So we can have a format that we can parse, mainly transforming objects with dynamic fields into arrays. So we will run our parse script and then copy the modified JSON. Now, I have a local chain here with Mythos, and I have a dApp here. I've already uploaded our state machine interpreter here, and we already have a dApp, and this is the address of the state machine interpreter smart contract, so we can execute transactions from here. And if we look at what functions our contract exposes, it's create, which creates a new state machine, run, which triggers an event that executes state transitions, and then some functions here for looking at the current state and current context, get current state and get context value. So we will be calling the create function with the JSON object that we just produced. And now we will execute this transaction. We get our transaction receipt. We can take this transaction hash, go to our explorer for our local chain, and see the transaction here. Now we see this data, which is the result of the create function. We can copy it and decode it here. And we see the ID is 1. This is the ID given to our machine. So now let's see our current state. And we'll put ID 1 for our machine. This is a query, and we see that our state is unlocked. This is what we expected. And if we look at our counter value, we should see 0, which is exactly what we get. Now, we can use the run function with the increment event. And this is a state changing transaction. We can execute the transaction. And look at the transaction hash if we want. And now if we again look at the counter value, we see that the value is 1, so it has been incremented. So let's run the increment event one more time. And then get the counter value, and it is 2. So now let's trigger the lock event. And this is a state changing transaction. So if we look at the current state now, it should be locked. And it is. So if we will try again to trigger the increment event, this should fail. And we see that our contract reverted. So you can create smart contracts visually and leverage state machines to increase both human readability and pattern recognition in smart contracts. State machines make it easier to avoid entire classes of issues like reentrancy attacks. And in future demos, we will introduce more features like guards and show you more complex examples.